So this is our first truss example, and the first thing we're going to do is actually analyze the whole truss system. Usually this is the first step for trusses as well as machines and frames. So I'm not gonna redraw this diagram. I'm just gonna keep it how it is. So what we have here, we have a roller, and we have a pivot here, and we're told to find the force in every element, so every two force member, and determine if the two force member is in tension or compression. So if we look at the reaction forces of this whole diagram, what we have here is that we have a normal force due to this roller, we'll call EY, and then we have a reaction force going in the X and Y direction of the pivot, so we'll call this DX and DY. And I'm defining these arbitrarily. You could define them in other ways. As long as you're consistent with the mathematics and you're consistent with your signs, you should still get the same answer. So that's the diagram right there. And also we're going to define these angles. So we're going to say this is theta, and this is going to be theta as well, and this is going to be right here. We'll say this right here is going to be alpha. And I know this diagram is not drawn to scale because this 4 meters doesn't look like this 4 meters, but just assume they're the same. So let's define these angles real quick. So I'm going to start with the angles. So we're going to define theta as theta equals the tan inverse of 6. So it's going to be opposite over adjacent, which is 6 over 4. So it'll be 6 over 4. And then alpha is going to be the tan inverse. So if this is going to be that right triangle, something that looks like that, this length right here is going to be 6 minus 4, so that's 2. So that's going to be 2 divided by adjacent, so it's going to be this length, which is going to be 8. So this is what I get for the angles, and we're going to use that later to solve this problem. So back to what I was saying before, what we're going to do is analyze this whole truss system and see what we can get from these values EY, DY, and DX. So the first thing I'm going to do, I'm going to change color, so I'm going to say this color, and we're going to sum the forces in the X direction. So what we're going to do is sum the forces in the X direction. So sum of the forces in the X direction. If we look at this diagram, the only force acting on this full free body diagram is dx. There's no other x component, so we just write that value. So dx is pointing in the negative x direction, so we'll set that equal to 0. And what we can say is that dx actually equals 0. So what we can actually do is eliminate this this force because it has nothing to do with it. So actually I'm just going to scribble it out. So now we look at the sum of the forces in the y direction. So let's look at that. Sum of the forces in the y direction, what we have is going to be EY plus DY minus 5 kilonewtons minus 6 kilonewtons equals 0. If you're wondering where I get that, it's from this diagram. So plus DY plus EY minus 5 minus 6. And we could set up an equation. So it'll be EY plus DY equals 11, and this is in kilonewtons. And then the last thing we're going to do is actually take a moment. So what moment we can do? So we want to take a moment about a point where it eliminates one of these variables. So we could take the moment about D or the moment about E. But in this problem, I'm going to take a moment about E. So we're going to get rid of that E variable. So we're going to say the moment about E, and we're going to say counterclockwise is positive. So what we get positive rotation for this 6 kilonewtons, we get a positive rotation for this 5 kilonewtons, and we get positive rotation for the dy force. So we apply the concept of moment, so we get 6 times 8 plus 5 times 4 plus 4 times dy equals 0. And we could solve for dy by simply doing some algebra. So we get 4 dy equals negative 68. And we get dy equals negative 17 kilonewtons. And we get a negative answer. That just means I drew this reaction force in the wrong direction, which is completely fine. I'm not going to change any directions of the forces until I'm done with the problem. So I'm going to keep the negative sign and just continue to do the math. So So what we have now, we have negative 17 for dy, and we say that ey plus dy, so that'll be minus 17 equals 11. I'm using this equation right here, plugging dy into this equation, solving for ey. So what we get for ey is equal to 28 kilonewtons. So now we have the values for ey and dy, which are the reaction forces of the system, and we can use that later to actually solve this problem by using the method of joints. So that is a very crucial thing for truss problems or machine problems or frame problems, is actually look at the whole system and draw a free body diagram of that whole system and analyze it first and see how many variables that you can eliminate and solve for, which can save time later when solving the problem. To make this video a little bit shorter, I'm just going to jump ahead and draw and show you guys the free body diagram of this truss. That means just exploding this diagram into its various components, meaning the two force members and the joints. Remember, you could draw the reaction forces between these two force members and these joints in any direction that you want, as long as they're pointing in the axis of the member. Just remember, because that's the definition of a two force member. And just so you could draw them in any direction, and again, as long as you're consistent with your signs and you do the math correctly, you should get the same answers that I do. So I'm just going to jump ahead to the free body diagram. Okay, so this is how your free body diagram should look like. I know this is very tedious. Some professors actually just teach it and just looking at the joints themselves, but the only reason I don't like that is because sometimes it's kind of counterintuitive on whether a member is in tension or compression, because if it seems like if you drew just the joint and you show this force FFC pointing in this direction, you might think, oh, the bar or this two force member is actually in compression, when in reality it's actually in tension because you drew the force in this direction. So drawing the free body diagram in this sense allows you to actually see whether a two force member is in tension or compression. Again, this is what it should be looking like on your paper. Again, it doesn't matter whether you draw these reaction forces the same way as I did. As long as you're consistent with your signs and did the math correctly, you should still get the same answers that I get. So the first thing we're going to do is actually look at the joint D. We're going to start with joint D and analyze it. And the only equations that we're going to use is basically the sum of the forces in the x direction and sum of the forces in the y direction. So what we're going to do is sum the forces in the x direction of joint D. So joint D, what we get, so we look at joint D, we're going to get the sum of the forces in the x direction. We get positive, I'm sorry, this is off screen, positive FCD minus FDE cosine theta equals 0. And then you get FCD equals FDE cosine theta. And that is then we could define some of the forces in the y direction. So we sum of the forces in the y direction, we get dy, which we found earlier, minus FDE sine theta equals 0. And now we're going to solve for FDE. So FDE is actually equal to dy over sine theta. And we said that dy is actually negative 17 kilonewtons over the sine of 56.310 degrees. And the reason why I'm using negative 17 kilonewtons is because I kept the same force vector for the reaction force at pin D. I kept it in the same direction. So I have to use the same value for dy that I found earlier when I took the moment about E. So I'm going to have to use negative 17. That's why it's very important to be consistent with your diagrams. If you can switch this value to a positive value, but you would have to draw this dy reaction force pointing downward, and then you proceed with the mathematics. But other than that, just keep the signs and keep the same free body diagram throughout the whole problem, and then at the very end, if you have to, change the direction of the forces. So what I get for FDE what we get, FDE is actually equal to negative 20.431 kilonewtons. And what we can say for FCD is that it equals negative 20.431 kilonewtons times the cosine of 56.310. And FCD would then equal negative 11.333 kilonewtons. So now we could describe whether this two-force member or these two force members are in tension or compression. So they're both negative, and these are members DE and CD. So this is negative, the force vector is negative. This means this right here is actually in tension. We just basically flip the sign of the arrows. Or yeah, flip the arrows because of the sign. So the force vectors are actually pointing in this direction. And this bar, this would also be flipped because we get a negative value for the force, so that means this is actually in compression. Sorry for my sloppy handwriting. So now that we have that, we can continue with the problem. And the next joint we're going to analyze is joint E. And I'm going in an arbitrary fraction. You could analyze another joint if you prefer, but usually it's best to have no more than two variables when solving the next joint. If you have more than two, then you might have to use system of equations to solve it, and that may be an issue. So, or more than three variables, which cause a system of equation with three equations instead of two, which may be an issue. Just makes your life a little bit more difficult. So just choose joints that you know that will have two or less variables. So for joint E, we're going to sum the forces in the x direction. So there'll be sum of the forces in the x equals FDE cosine theta plus FAE cosine alpha equals 0. And then we could say FAE is equal to negative FDE cosine theta over the cosine of alpha. So if we plug in some values there, so what I get for FAE is 11.682 kilonewtons. So now what we can do is actually sum the forces in the y direction. So sum the forces in the y, what we get is EY minus FCE plus FDE sine theta minus FAE sine alpha, and that equals 0. And if you're, again, I'll probably put an image or something so you guys could see what I'm doing with the forces in these equations. So what I can do is actually solve for FCE. So FCE is equal to EY minus FAE sine alpha plus FDE sine theta. And if we plug in some values, what I get for FCE is equal to 8.167 kilonewtons. So FAE and FCE are positive, so that means we drew the reaction forces in the correct direction. So FCE is positive, so that means this is actually in compression as drawn here. So I'm going to put compression. So that is correct. And then this is also in compression. We drew this correctly as well. So the next joint we're going to look at is joint C, and we're going to analyze that by using the two equations we've been using before. So the first thing we're going to do is actually sum the forces in the y direction. So for joint C, I'm running out of room here. So sum the forces in the y. This is going to be FCE minus FFC sine 45 degrees. And if you're wondering where I get this 45 degrees, this side is equal to this side. So these two sides are equal, and this creates a right angle, that must mean this is a 45, 45 triangle. And again, I know this image is not drawn to scale or perfectly to scale, so just imagine this length right here is the same as this length right here. I know that might throw you off a bit, but just imagine them the same. So now that we know that, what we can do is continue with the problem. So we could say that FFC is equal to FCE over the sine of 45, and that equals 8.167 over the sine of 45 degrees, and that is 11.550 kilonewtons. And then we can sum the forces in the x direction, so we get FBC minus FCD minus FFC cosine of 45 degrees equals 0. And after doing some algebra, I could say that FBC is equal to negative 3.16 kilonewtons. So BC is negative, so let's go to our diagram again. BC, where's BC? BC is right here, so it's negative, so we could say that is in tension, not compression, because we have to flip the arrow because it's negative, and we could say that this right here is also in tension. So because this is positive, the force value for FFC was positive, so we could say this is in tension. We're almost done with this problem, so the next joint we're going to look at is joint F. So that's this joint right here, and we're going to look at the sum of the forces in the x and y directions. So for joint F, we're going to label it as joint F, and then we're going to say the sum of the forces in the x direction, that's going to be FFC cosine of 45 degrees minus FAF, which equals 0. And we could say that FAF equals 8.167 kilonewtons. And I'm going a little bit more quickly because I think you guys understand the process now. So we get that, and then we're going to sum the forces in the y direction, which is going to be negative FFB plus FFC times the sine of 45 degrees, and that equals 0. And then we could solve for FFB, which is going to equal 8.167 kilonewtons. So what we can say now is both these values are positive, so that means we drew the forces correctly on the diagram. So we can say that FFB or FB is actually in compression, and we could say that this member right here is in tension. And the last thing we have to solve for is this FAB force, which we could analyze either joint B or joint A. It's up to you. I chose to analyze joint B, so that's what I'm going to do. So we're going to take the sum of the forces in the x direction of joint B, and that's going to be FAB cosine of 45 degrees minus FBC, which equals 0. And we're going to say that FAB, which is the last force we need, is actually negative 4.477 kilonewtons. So we drew the forces incorrectly on the diagram. So what I can say is that this is actually in tension. And there you go. We solved this truss by analyzing the forces within the two force members and the joints. And actually, the most important thing that people forget is to analyze the whole body without exploding it into various parts. So I'm going to quickly review what we just did. So the first thing we did was define the angles we need for the various forces. So we defined angle theta and angle alpha, which is here. And then we looked at the free body diagram of the full truss. And that should always be the first step for machine, truss, or frame problem. because it allows you to apply the basic ideas of equilibrium. The sum of the forces in the x direction, the sum of the forces in the y direction, and moment. And we use that right here to actually figure out that the reaction force at the pin in the x direction is equal to 0. And we found two equations for the reaction forces Ey and dy, and we solved them without actually having to break up this whole truss into various pieces and solve them using the method of joints. So that helps us in the long run because now we have less variables to deal with and we can solve the problem quite easily. And then what we did next was actually explode the diagram or explode the truss into its parts and drew the reaction forces. And then again, professors usually just look at the joints themselves and that's all they draw. I like to draw the whole thing because sometimes it's confusing when determining whether the member is in tension or compression. Because let's take, for example, this reaction force FFC. If you were just looking at the joint, you might assume that the member FC is actually in tension or in compression because you drew the force in that direction. So you would think it's in compression because you drew the force in this direction, but actually it's in tension because the reaction force on the two force member points in the opposite direction. So it's always best, in my opinion, although it's longer, is to draw the whole diagram like this. And then from there we just analyze the various joints one by one, which is very tedious, but you systematically choose or strategically choose the joints and in an order that allows you to solve these problems or solve these joints with two or less variables. If you have three, then you might have to analyze two joints before you can actually get any numerical values. So and then we just repeated that process until we found that every member is in tension, or whether a member was in tension or compression, and we found the forces reacting through it. Oh, and very important to know is that you keep the signs that you have solved for within the various joint sections. So if you say, if you drew the diagram like how I did, and you say like maybe this force FFC was negative, just keep the negative value. Don't actually change the free body diagram. Keep it the same and just plug in the negative values in your other equations. Just keep the diagram the same and change it at the very end if you really have to. That is probably the crucial trick and probably the most missed thing when it comes to truss problems. So that is the basic idea of a truss problem. This is very tedious, but if you understand this, then you could solve practically any truss problem. However, there are still tricks to be applied, such as symmetry and zero force members, which we'll get to in the future problems.